Now let's talk about combined circuits and how we can solve it. Over here we have an example combined circuit. It's a combined circuit because it has a parallel circuit and series circuit. So the properties we just discussed apply to for both series circuit and parallel circuit apply to this circuit. So how will we solve it? Well, first let's look at the current and the way it travels. Starting from the battery. The current exits the battery with 9 volts, meets the junction point, and splits into two. It then meets back together at the second junction point, goes through one resistor, goes through another resistor, and travels back to the battery. So let's break it down step by step and see how we can solve it. First, we need to find the equivalent resistance for the parallel circuit. The equivalent resistance will be the inverse of 1/2 plus 1/2, which is just 1. The equivalent resistance for the parallel circuit, let's make it one big resistor, will be 1 ohm. Now we have these two. We know that the equivalent resistance of the resistors in a series circuit is the sum of the resistors. 1 ohm plus 1 ohm plus 1 ohm, 3 ohms. The grand total equivalent resistance for this combined circuit is 3 ohms. Using Ohm's law, we can solve for the current that exits the battery. 9 volts equals 3 ohms. 9/3, or 3. The current is 3 amps. Now, let's go back to the parallel circuit. Recall that the equivalent resistance for the parallel circuit is 1 ohm. As the current passes, the voltage dropped by the total voltage dropped by the equivalent resistance will be equal to the current, which is 3 amps, times the equivalent resistance, which is 1 ohm, so 3 volts. In a parallel circuit, the voltage drop is the same for both the paths. So the voltage drop will be 3 volts here, and the voltage drop will be 3 volts here. Next, the current will then